Hello everyone, welcome back to CPE 517-WS Digital and Computer System Architecture course. This is part 4 of lecture 7. We talk about dynamic scheduling, or typically the specific example Tomasulo's algorithm theory. Okay, dynamic scheduling. So what is dynamic scheduling? Okay, dynamic scheduling rearranges the execution of the instruction using the hardware. Doing so, we want to reduce the stalls while maintaining the data flow and exception behavior. It handles the cases when dependencies are unknown at compile time. So we know that in compiler time, we do some loop unrolling, we do some instruction reordering, etc., etc. But actually, there's a lot of things that's unknown before we even execute it. So only when we execute it, we know what's going on there. This is the place where hardware-based dynamic scheduling and later speculative execution we're going to talk about next lecture used. So dynamic scheduling allows the processor to tolerate some unpredictable delays due to dynamics, right? Like cache misses, by executing other code while waiting for the miss to resolve. It allows the code that compiled for one pipeline to run efficiently on another. It simplifies the compiler, right? Hardware speculation is another technique which has a significant performance advantage, is built upon dynamic scheduling. Dynamic scheduling definitely is very important, okay? Hardware schemes for instruction parallelism. This is an example like code snippet. So what we do is we allow the instructions behind the stall to proceed earlier. For instance, we have a division of F2 by F4 and write the result to F0. And then we add F0 and F8 and put a result into F10. Later we do subtraction. And using F8, subtract F14 and put a result into F12. As clearly we can see that the add of the double word F0 and F8 going to take a lot of time to wait until division to finish. So basically, this instruction gonna have a lot of stall due to data hazard, right? And then this subtract double word instruction is very fast, should be. But due to the sequential, like a pipeline nature, maybe this instruction gonna be pending on the structure hazard or finish of the second instruction. So that's not good. So what we're gonna do is we're gonna enable our dynamic scheduling hardware-based scheme, gonna enable out of order execution as well as out of order completion. In a dynamically scheduled pipeline, all the instructions still pass through each issue stage in order, but they can finish and complete, execute and complete in order. We will distinguish when an instruction begins execution and when it completes the execution. Between the two times, the instruction is in execution. Dynamic scheduling creates dynamic execution creates right after read and right after write hazard, because, for example, this instruction can finish earlier. So maybe there's a right after read and read after write problem, or read right after read and right after read, right after write. Previously, this is okay, but once it goes to dynamic scheduling where we allow out of order execution and out of order completion, this could be a problem. So in dynamic scheduling, we include 3 steps we're going to talk about later. Simple pipeline had a 1 stage to both structure and data hazard. In instruction decoding, we also call that instruction issue. We split the instruction decoding pipeline stage of 5-stage pipeline into simply 2 stages. The first is issue. We decode the instruction, check for structure hazard, and read operands. Wait until no data hazards, then we read operands. A dynamic scheduling algorithm is the Tomasulo's algorithm. Tomasolo's algorithm is created in 1966. It's actually very, very popular. It is even have a significant impact, long-lasting impact even on today's computer using reservation station. The goal of this is that we want to achieve high performance without special compilers. Basically, because we have very few number of registers, if we do compiler based optimizations, we need a lot of registers to do register renaming. Well, actually, we only have 4, right? Then we have to figure out more effective ways for register renaming. And that is in the hardware. So we don't do losing hardware, don't lose compiler registers, or we don't abusively use registers, right? So we have to use it very efficiently and effectively. The descendants of this have flashed, right? We have a lot of computers, even today's computer, somehow depend upon dynamic scheduling, Tomasolo's algorithm. So what is Tomasolo's algorithm? First thing first, we see in the right side of the figure, it has a couple of operations, and this operation can go to loading, storing, right? Loading, storing, or adder, multiplier, or probably divider. And then it also can go to registers. Once the finished, it use common data bus to communicate across loader, adder, multiplier, memory, and floating point register. So we can say it seems like what we are doing here is trying to use the common data bus to communicate information across all the function units, right? The loader, adder, multiplier, store, and register, right? So these function units together collectively called reservation station. They have pending operands. So what do we mention about in data dependency, anti-dependency, output dependency, et cetera, those kind of dependencies, or structure hazard, those things are perfectly resolved by this reservation station. Registers in the instructions are replaced by values or pointers to reservation station called register renaming. This renaming avoids write after read, write after write hazard, and also automatically detect the data hazard, right? So the results to function units from reservation station are not through register communication anymore. It's through common data bus that broadcasts the results for all the function units, so that all the function units that has the write after read. So we have 3 hazards, right? Write after read hazard will be notified by this providing of the information. So what we're gonna do is after 1 cycle delay, the next instruction that depending upon the results of the function unit would proceed forward. Okay, so as you can see here, the reservation station solves what? Structure hazard, right? Structure hazard, because it has multiple adders, multipliers, stores, loaders, and so different like people who is counting on that, different instructions that counting on different function units can proceed. Second, data hazard, like read after write, and we use the common data bus to provide the data and broadcast the data to the function units. So now the function units only need 1 cycle delay to move forward, right? And then it also combat the anti-dependency, that is write after read, and output dependency, that is write after write. Okay. Well, we have to be clear that dynamic scheduling cannot go past branches. Okay. The reservation station has a couple of important components here. First, it has right? Operations to be performed in the unit. VI, VJ, and VK, the value of the source. QJ and QK, the reservation station producing the source registers. Okay. Busy indicates the reservation station or function unit is busy. So a value V can be value, Q can be query. You can think of that way. Query is like I'm needing something, I need your help. Or value is the source where it has the value, right? Register result status indicates which function unit will. I have to be clear that this is not for dynamic scheduling. Dynamic scheduling does not go past branch instructions typically. Branch instructions has to go either to static prediction. If it's static prediction, like I always predict taking or not taking, it is okay. Oh yeah, yes, this is true. So if you always predict taken, then it's definitely allowed. But you cannot do speculative execution, which is will be taught next lecture. Okay. So when it's a static prediction, then it's like a single basic block, right? Because it's always like that. Register result status indicates which function unit will write each register if one exists. Blank when no pending instruction that will write to that specific register. This actually notifies, serves the intermediate to notify those guys who, which instruction they should depend upon. The 3 stages of Tamasulu's algorithm are issue, execute, and write results. Issue, get an instruction from the FP issues here. It gets the instruction from FP operation queue. If reservation station is free, control issue owns instruction and sends operands. Execution operate on operands. When both operands ready, then execute. If not ready, watching for the common data bus for the results. Writing results, finish the execution, write on common data bus to or awaiting units, mark reservation station as available so that the structure header can be resolved. Normal data bus is data bus plus destination. Common data bus is the data bus plus the source coming from where it come from, right? So this is very different. So once like a common data bus is like for broadcast, normal data bus is for where the destination should go. So what we want to discuss next is we'll tell you how the readback will actually trigger the instructions that is counting on these results to go forward. Like when we write the specific instructions and then how the QI and QJ will be triggered, okay? Because the stores or where the source comes from. So when the source comes in and then this is gonna be notified. So this QJ and QK will be clicked, like switched. That how it triggers the instructions that are waiting on, that wait on this finish the completion of these sources to proceed forward. So taken together, this actually is a very similar like a hardware managed buffer of producer and consumer, right? So when I'm a consumer and I'm waiting for some data, so what I'm gonna do is I'm gonna observe that specific register. Whenever that register is updated, it's like a spinning, right? So that register update will notify me, so I'm gonna proceed forward. Okay. We're going to use an example in this part 5 to explain, but for this part 4, this is okay.